Hello and welcome to Electromagnetics 1. Dr. Trampel here. This is lecture number 7. We're going to be talking about the electric potential and Laplace's equation today. Well, it turns out that in the electrostatic case, in other words, when there's no time variation and when we're concerned with the electric field rather than the magnetic field, we can obtain the electric field in 3 ways. We've talked about the first 2 in previous lectures. The first approach is Coulomb's law, which works for any charge distribution in principle, but can be difficult for complicated geometries. The second is Gauss's law, which we talked about in the last lecture, and that's a good way to obtain the electric field for symmetric charge distributions. And the third approach will be the subject of today's lecture, which is we can get the electric field from the electric scalar potential V. This is voltage that you learned about in circuits class. Well, let's start our journey toward defining the electric scalar potential here by recalling the 2 Maxwell's equations for electrostatic fields. The first one is this modified version of Faraday's law right here, which says that the curl of the electric field is 0 under electrostatic conditions. And the second is the Gauss's law right here in differential form, which says that the divergence of the electric flux density here is equal to the volume charge density in that region. Okay. Well, let's start with Faraday's law, and we're going to apply Stokes' theorem to Faraday's law in this way. So if you remember, Stokes' theorem says that the curl of a vector field integrated over an area is equal to the circulation of that vector field around the border surrounding that area. Okay, and because we have a 0 on the right-hand side of this equation, it turns out that the circulation of the electric field is equal to 0. And if the circulation of a vector field is equal to 0, we call that vector field conservative. So this is a definition here. This is an equation that conservative fields will always satisfy. Well, how can we take advantage of the fact that the curl of the electric field here is equal to 0? If you recall the irrotational theorem, we're going to be applying that in this case. The irrotational theorem here applied here says essentially that let E be a vector field, so in other words, let the electric field be a vector field. If the curl of E is equal to 0, which it is in our case, there exists a scalar potential V such that the electric field can be written as simply the gradient of that scalar potential. And here I've added the negative sign, which is there by convention. But this really is a consequence of the fact that the electric field has no curl. And so therefore, for any vector field that has no curl, the irrotational theorem says I can simply express that vector field as the gradient of a scalar potential. Okay. This is important because generally speaking, it's much easier to work with scalars than vectors. So eventually what we'd like to do is simply work with this scalar potential, which essentially work with the voltage. And then after we've solved for the voltage for a particular geometry, we can use this equation, take the gradient, multiply by -1 to obtain the electric field. It's just a simpler approach to a lot of problems. Well, okay, let's say that we integrate the electric field along a line and apply the fundamental theorem of calculus for line integrals. Okay, that's the next thing we're going to do. Okay, so let's just simply say that we take the electric field and we integrate it along a line connecting a point indicated by R1 and a point indicated by R2. Well, we can substitute now in the electrostatic case for the electric field here. That's all I've done in this next step. I'm just simply saying the electric field is minus the gradient of the potential. All right. And if you remember, the fundamental theorem of calculus for line integrals, which I introduced in the, I believe in the differential vector calculus lecture, says that if you integrate the gradient of a scalar potential like this from R1 to R2, then basically what pops out is just simply that potential evaluated at the endpoints. Okay. So this tells us something about what the scalar potential, what the voltage V actually is. The voltage V between 2 points, the potential difference, in other words, between 2 points, is literally equal to the line integral of the electric field between those 2 points. Okay, and it turns out because the electric field is conservative, it just turns out that the path that we take between point 1 and point 2 doesn't affect the potential difference. In other words, we will get the same potential difference between 2 points no matter what path I integrate the electric field along connecting the 2 points. So that's important. That's a consequence of a conservative electric field. Okay, let's look at the electric potential here for some specific geometries. And let's start off with the simplest one you could imagine, which is just simply a point charge. So we've got a point charge Q sitting here at the origin, and we would like to know what is the voltage out here at a point R away from the origin. Well, you can use Gauss's law, and we didn't do this in lecture, but it's in the text. You can use Gauss's law to show that the electric field due to a point charge is spherically symmetric. In other words, it doesn't depend on theta or phi. It's spherically symmetric, and it falls off as 1 over r squared. Okay, and it points radially out from the point in the r hat direction. That's straight from Gauss's law. Well, let's find the potential difference between 2 points in space here due to this electric field. And again, we're just using the definition from the previous slide that this potential difference is equal to the line integral of the electric field. Okay, so we're integrating the electric field between 2 points along a line radiating out from the origin like this. So for instance, point A might be at this point and point B might be out here. So, but it's the point is that both points are located somewhere along the line radiating radially out from the origin. Okay, so along that line, E dot dl takes this form. So here's the E right here, and dl looks like this. Dr dot r hat. Okay, and when you take r hat dot r hat is 1, and so you just end up having to integrate 1 over r squared, and that is minus 1 over r. And so when we evaluate it at the limits, we get this expression right here. 1 over the radial distance from B minus 1 over the radial distance from A. And if we're concerned with the case of the radial distance of A tending to infinity, we end up with this expression. Okay, so in other words, if we allow the A point essentially to be pushed out to infinity, we get an expression for the electric scalar potential of a point charge located at the origin right here. So at any point here on a constant radius, the electric scalar potential looks like this. It's very similar to the electric field, except of course it's a scalar, not a vector, and the magnitude of the potential falls off as 1 over r, 1 over the radial distance versus 1 over r squared. Well, just like we had a principle of superposition for the electric field, there's a principle of superposition for the electric potential. Okay, and I'm not going to belabor this too much, but I think you can see that since these fields are linear, if instead of having a single point charge, I have n point charges, as in this case, that I can simply, if I want to know the electric potential at a point r, an observation point r out in space, then I just simply add up all of the potential due to all of the n charges. That's it. And so that's an expression for that right here. This distance here just gives you the distance between each particular charge and the observation point. Okay, and we have very similar expressions for continuous charge distributions. Again, if instead of having point charges, we have a continuous charge distribution, for instance, a line charge density, a surface charge density, or a volume charge density, then we can find the voltage due to all of those charges using these integrals. If you notice, they look, again, qualitative, they look very similar to the expression for the discrete case. We just have to deal with the fact that we've got a continuous distribution, and so that means we have to do an integration. But you'll want to compare these three expressions to the expression for the electric field due to continuous charge distributions. You'll see they're very similar. The biggest difference is, again, it's a scalar rather than a vector, and the magnitude of the potential due to some little differential charge falls off as 1 over the distance between that charge and the observation point. Okay, well, as I mentioned before, for an awful lot of situations, we would like to work exclusively, if we can, with the scalar potential rather than with the electric field. So let's see if we can come up with an equation governing the electric potential that we can solve. All right, and the beginning place for that is just simply, again, Gauss's law in differential form right here. The divergence of the electric flux density is equal to the volume charge density. All right, and so now we're going to play a similar game. We're going to substitute for the electric field. We're going to use the expression that the electric field is equal to minus the gradient of the potential, and we're just going to substitute that right in here. And what we end up with is minus the divergence of epsilon times the gradient of the potential. And there's a vector identity that says that the divergence, the gradient in this case, is equal to the Laplacian, okay, in the case where you have an irrotational field, which we do in this case. So divergence of the gradient in this case just leads to the Laplacian of the potential, and this is the scalar Laplacian here. It's operating on a scalar, okay. So the Laplacian of the scalar potential V is equal to minus the charge density at that point divided by epsilon. This is called Poisson's equation. Now, a special case of Poisson's equation that occurs if the volume charge density is 0 is called the Laplace's equation. So if you're in a region that does not contain charges, the electric scalar potential satisfies the Laplace's equation, which is basically the Laplacian of the potential is equal to 0 in that region. Well, let's look at a problem where we would like to solve for the electric scalar potential. Okay, and this is an infinite conducting box. I think the text calls it an infinite conducting trough. So in other words, it's infinite here. You can see this is the x direction along this way, and this is the y direction along this way, and so it's infinite in the z direction coming in and out of the screen. So it's infinite in that direction. Okay, and so here's the problem. What we have here is we have 4 different sides to our box. The top side is going to be held at some potential V naught, some non-zero potential V naught. Okay, and the sides and the bottom are going to be held at a potential of 0. And what we would like to know is what is the potential here, what is the voltage, quite literally, inside of our box. Okay. Well, there are no charges inside of the box. I should have said that before. There's no charges inside of the box. So what we have to do is we have to solve this equation right here. We have to solve Laplace's equation subject to these boundary conditions. In other words, when x is equal to b, for any value of y, the potential needs to be 0. When x is equal to 0, for any value of y, the potential is 0. When y is equal to 0, for any value of x, the potential needs to be 0. And when y is equal to a, for any value of x, the potential needs to be v naught. So that's our task. Solve this partial differential equation subject to those 4 boundary conditions. And there's a uniqueness theorem that says if you solve Laplace's equation subject to a particular set of boundary conditions, you get a unique solution. It's called the uniqueness theorem. Well, in Cartesian coordinates, this is a Cartesian coordinate problem. The Laplacian looks like this. Okay, in general, this is the most general expression for the Laplacian, the scalar Laplacian in Cartesian coordinates. Okay, we get a little bit of a simplification in this case because the geometry is invariant in the z direction. We have translational symmetry in the z direction, and so therefore the partial derivative of the potential with respect to z is equal to 0. There's no change in the potential in the z direction because the geometry doesn't change at all in that direction. There's no reason for the potential at one value of z to be different than at another value of z. So that translates to this derivative being 0. And so therefore this term in the Laplacian falls out, and we just have this equation that we need to solve. Okay, partial second derivative with respect to x, a partial derivative, the second partial I should say with respect to x plus the second partial with respect to y of the potential is equal to 0. So this is the equation that we need to solve. How are we going to go about solving it? We're going to use a technique called separation of variables. Okay, essentially what we're going to do is we're going to expand our unknown electric potential V into the product of 2 functions, capital X and capital Y. Capital X only depends on the x coordinate. Capital Y only depends on the y coordinate, like that. All right, and then we're going to substitute this trial solution into this differential equation right here. Well, when you do that, you get 2 ordinary derivatives with respect to x here on this term, okay, times y of y, plus 2 ordinary derivatives here with respect to y times x of x, okay. And we can divide both sides of this equation by the product x times y, and what we get is the following. This ratio is equal to the negative of this ratio here, okay. And the usual approach then is this is we've essentially got two equations here. Well, it's one equation, I should say. The left side here only depends on x. The right hand side only depends on y, okay. And the argument is for them to be equal for all values of x and y, then they need to each be equal to the same constant lambda. This is called the separation constant, okay. So once I introduce the separation constant, then in fact x double prime over x is equal to lambda. We can rewrite that equation in this way, and also minus y double prime over y is equal to lambda, and we can write that equation in this way. Okay. So by introducing, by using the separation of variables technique, we are able to convert our partial differential equation into 2 ordinary differential equations, just like this, that we can solve. Let's work on solving this first one involving the x coordinate. There are 3 different cases involving the sign, or I should say just simply involving this separation constant lambda. We can have lambda less than 0, we can have lambda equal to 0, and we can have lambda greater than 0. It turns out that for this particular case, that if lambda is less than 0 or if lambda is equal to 0, we just end up with the trivial case that the potential everywhere is equal to 0. That's of no interest to us. Okay. But the third case, which is lambda positive, we get a non-trivial solution. So that's the case that I'm going to focus on here. Cases 1 and 2 are in your text. If you want to explore those on your own, I'd encourage you to do that. It's advantageous here for lambda positive to set lambda equal to the square of beta. So we're just simply converting our separation constant into the square of a second separation constant, essentially. Okay, and so we're substituting in here lambda equals beta squared into our ordinary differential equation for capital X. Okay. Well, if you look at this, a second derivative with respect to x of this function plus some constant squared times that function itself is equal to 0. That's simply a harmonic equation, and it has sinusoidal solutions. Okay, so we can say that, and you can satisfy that if I satisfy yourself that if I substitute this form of this function into this equation, that this equation is in fact satisfied, that the left-hand side will be equal to the right-hand side, which will be 0. Okay, so in other words, what we're going to do is we're going to say, well, this function capital X of x is equal to some constant times cosine of beta x plus some constant times sine of beta x. All right. Now the question is, what's beta, what's C1, and what's C2? Okay. Well, let's work now with our boundary conditions. The first boundary condition of interest is that the potential at x equals 0 for any value of y has to be equal to 0. Okay. So when we substitute x equal to 0 in here, sine of 0 is 0, so this term falls off, and what we end up with is this equation, C1 is equal to 0. Okay, so cosine of 0 is 1, and so in order for this potential here to be 0 for any value of y, turns out that this coefficient C1 needs to be equal to 0. So we modify our trial solution by simply removing this term. Okay. Now we have a second boundary condition involving the x-coordinate, which is that when x is equal to b, the potential also has to vanish. So now we substitute in b here and say that the function must be 0. So x at x of b is equal to 0 implies C2 times sine of beta times b must be equal to 0. Well, if we set C2 equal to 0 here, in order to satisfy this equation, we're going to end up with a trivial solution again. X of x everywhere will just be equal to 0. That's of no interest. But what we can do is we can modify this beta such that this equation is always satisfied. So in other words, if beta times b is equal to some multiple of pi, where n here is an integer, then this equation will always be satisfied. So in other words, beta times b must be equal to some integer multiple of pi, which means beta itself must be n pi over b. Okay. So here is the trial solution for our x function so far. It's equal to some unknown coefficient, we don't know what g sub n is at this point, times sine of n pi over b times x. I've just simply substituted now for the beta that we found here. Okay, so this is our trial function for x. Now the question is, what should our y function be? That's the next question. And remember, the y function satisfies this equation. It's the same as the x except for this sign right here. Well, it turns out that if this is my beta, and beta squared is equal to lambda, it turns out that in order to satisfy this equation, I need to use hyperbolic cosines and hyperbolic sines. Okay, if you're not familiar with these functions, make sure to look them up. But essentially, instead of oscillating, so instead of this function oscillating sinusoidally in the y direction, it's a sum of exponentially increasing and decreasing terms. Okay, same here. Instead of oscillating in the y direction, it's a sum of exponentially increasing and decreasing terms. Okay. You can again satisfy yourself that if you plug this equation, I should say if you plug this function in this form into this equation, again, the left-hand side will be equal to the right-hand side, which will be equal to 0. In other words, this function satisfies this equation. Okay. All right, still two boundary conditions to deal with. The first one is that the potential at y equals 0 for any value of x has to be equal to 0. Okay, substitute y equals 0 here and here and set this entire function equal to 0. That implies, again, because hyperbolic cosine of 0 is equal to 1 and hyperbolic sine of 0 is equal to 0, this term falls out, and what we end up with is h naught has to be equal to 0. So we don't have a hyperbolic cosine term in this solution. So this piece is now gone, and we're just working with this term next. Question is, again, what's h1? And so essentially, oh yeah, we'll get to what h1 is just in a moment. So what we do, again, this term goes to 0, and we set our trial functions for y now equal to some unknown constant times hyperbolic sine of n pi over b times y. All right. Now remember, our total solution right here, v, is the product of x of x times y of y. So we're going to take our trial function for x and multiply it times our trial function for y, and that gets us an infinite series. We have to sum, at least at this stage, we have to sum over all these integer n's, all right, because n in this equation here can be any integer. We don't know. So initially we have to sum over all of them to get the total solution, all right. So it's some unknown constant c sub n times sine of n pi over bx times hyperbolic sine of n pi over by. Okay. This function depends only on y, this function depends only on x. Now the only thing we have left to do is figure out what this coefficient c sub n is, and we're done. How are we going to do that? Well, one last boundary condition to take care of, which is that the potential when y is equal to a on the top surface there for any value of x has to be equal to v naught. All right. This is the only, remember, the top side is the only side that's at a non-zero potential. Okay. So again, now we're going to simply substitute in y is equal to a into this equation and set the left-hand side equal to v naught. And this is where we end up after doing that. You notice now y is equal to a, and we have v naught on the left-hand side. And the way we solve for these c sub n's is by taking advantage of some orthogonality properties of the sine function. Okay, so we're going to multiply both sides of this equation by sine of m pi over bx, where here initially m is not equal to n. These are two different integers. Okay, so here I'm multiplying both sides by sine of m pi over bx, and here's the sine over m pi over bx term on the right hand side. And then we're going to integrate both sides of this equation from x equals 0 to x equals b. On the right hand side, we have this product, and it turns out that we can use a property of this product which essentially says that if you have the sine of some integer times x times the sine of some other integer times x, and you integrate that function from 0 to pi, this integral is equal to 0 whenever m is not equal to n. Okay, and it's equal to pi by 2 whenever the integers are the same. All right, so we're going to take advantage of that, and we're going to say, okay, The only time we're going to get a non-zero contribution on the right-hand side is when m is equal to n. So the summation goes away then, and we just simply set m equal to n here on the left-hand side and on the right-hand side. And so now we have sine squared on the right-hand side, we have sine squared of n pi over bx, and on the left-hand side we have this integration just simply over 1 power of the sine. All right. And here's our nth coefficient here, c sub n. Okay. It turns out that this integral you can do analytically quite simply using a trig identity. All right. And this integral we can do integral of sine is just simply minus cosine. And so by carrying out this integration on the left-hand side and this integration on the right-hand side, we can solve for c sub n. All right. I'll leave that as an exercise for you to show that c sub n takes this form. Okay. It's equal to 4v naught over n pi times hyperbolic sine of n pi a over b when n is odd. Okay, you get a non-zero c sub n only for the odd integers like this, and it works out that c sub n will be 0 for even integers. Okay, so the final total solution here for the potential inside of this infinite trough is this expression right here. I've just simply gone back into this equation now, and I've substituted for the c sub n's that we found. And that expression looks like this. You can see again here, it's a product of a sine in the x direction times a hyperbolic sine in the y direction and some terms that come from this c sub n. And you notice, if you'll notice here, we're only summing now over the odd integers because c sub n is equal to 0 for the even integers. Well, what does this solution look like for a practical geometry? Okay, so here is a trough where I've set b equal to 4. So this is the x dimension here. All right, so it goes from 0 to 4, and the y dimension goes from 0 to 2, just like this. Okay, so it's a 4 by 2 trough essentially, and I've set the top side, the top potential here, v naught equal to 5 volts. Okay, and you can see this is a plot that I made using MATLAB, and I've uploaded the MATLAB script to do this, to create this plot to the Canvas website, so you can download this and modify it and try it for yourself for different dimensions. For instance, you can change these dimensions here to be whatever you like. You can change the top potential to be whatever you like, and so on. Okay, but you can see essentially what's happening here. This is a plot of the potential v sub x and y. So the potential is a function of x and y throughout the entire interior of the box, and you can see that the potential at the sides here and on the bottom is equal to 0. Okay, so that boundary condition is satisfied, and the potential along the top is roughly equal to 5. We've got a little bit of error here in the corners, and that's just due to the fact that I've used a finite number of terms in the series. Okay, so I haven't summed to infinity because you can't on a computer. So I've truncated the series, so we have a little bit of error, but essentially along the top surface, I should say along the top side here, the potential goes to 5 volts. So we've satisfied the boundary conditions everywhere, and inside here you can see what the potential is doing. It starts here at 5 volts, and while it's not entirely obvious from this plot, it essentially decays exponentially to 0 as you move away from this side in the y direction. So it decays exponentially away from 5 volts down to 0 volts here on the bottom. And the advantage of using MATLAB is that you can see exactly what the potential is doing at any point, which is very helpful and powerful. And so I hope that you'll take advantage of the opportunity to use MATLAB to make plots like this. What we'll be doing for the first lab is we'll be using the MATLAB code, which is essentially an analytical solution to this problem, to check to make sure that the numerical solution of this problem that we'll be doing in lab is correct. So make sure to download this script before we do lab 1, which is a finite difference approach to solving this problem. Okay, thank you for your attention, and I'll see you in the next video.